Good morning, everyone, and welcome to today's presentation. We're going to be exploring the fascinating world of viscosity, specifically within the USPNF standards. Today's slide introduces the chapter on viscosity, covering various methods outlined in the USPNF. We'll look into capillary methods, rotational methods, rolling ball methods, and pressure-driven methods. This overview will help us understand how viscosity is measured and why these different techniques are important. So, let's dive into the details and get started. Let's start with the introduction, where we'll explore the fundamental concept of viscosity and why it's so important across various industries. Next, we'll look at the different types of viscosity, helping us understand that viscosity isn't a one-size-fits-all property. Then, we'll discuss the necessity of measuring viscosity accurately, highlighting its critical role in quality control and process optimization. We'll also cover the measurement techniques, focusing on the different types of viscometers available and how they work. Moving forward, we'll examine the validation and calibration parameters that ensure our measurements are reliable and consistent. We'll then talk about the critical quality attributes related to viscosity, emphasizing what makes it a key parameter in product development. After that, we'll look at some of the key applications where viscosity measurement is vital, from pharmaceuticals to food and cosmetics. Finally, we'll go through the table of contents, which will guide us through the entire presentation, ensuring we cover all these important topics comprehensively. Viscosity is a measurable quantity that tells us about a liquid's thickness. Think of it as how resistant a liquid is to flow. For example, water is relatively thin and flows easily, meaning it has a lower viscosity. On the other hand, substances like honey or oil are much thicker and resist flowing as much, so they have higher viscosity. This concept was first discovered by a French physicist named Jean-Leonard Marie Poiseuille. Today, we measure viscosity using the metric system, and the units are called poise or Poiseuille, named after him. Usually, we see viscosity expressed in centipoise, especially because the viscosity of water at 25 degrees Celsius is nearly exactly 1 centipoise. Viscosity also reflects how a fluid resists deformation, whether it's shear stress or tensile stress. In simpler terms, it's the internal friction within the fluid that makes it resist change in shape or flow. You can think of it as the fluid's resistance to shear forces. Mathematically, viscosity is the ratio of shear stress to shear rate. This means that higher shear stress or lower shear rate results in higher viscosity, and vice versa. So, in summary, viscosity helps us understand how fluids behave under different forces, and it's an essential property for many applications across science and engineering. When we look at liquids, their viscosity can vary quite a bit. For example, water, which is relatively thin and runny, has a much lower viscosity compared to thicker liquids like honey or oil. This means that water flows more easily and with less resistance, while substances like honey or oil tend to be thicker and resist flow more. Understanding these differences is important because viscosity affects how liquids behave in different situations, whether it's in industrial processes or everyday life. So, recognizing how the thickness of a liquid influences its flow helps us better grasp the broader concepts of fluid dynamics. Welcome to this introduction slide. Here, I want to emphasize the importance of setting the stage for our discussion. First, we'll clarify the key points that will guide us through the presentation. These points are essential because they form the foundation for understanding the overall message. I'll explain each one thoroughly, but in a way that's easy to follow, so it feels more like a conversation than a lecture. Throughout this presentation, I'll highlight the most important concepts, making sure you see how they connect to the bigger picture. Our overall theme is about understanding how these ideas interrelate to help us achieve our goals more effectively. By the end of this introduction, I hope you'll feel prepared and engaged, ready to dive deeper into each topic. So, let's get started and explore these key points together. Now, let's explore the two main types of viscosity. First, we have kinematic viscosity. This measures how viscous a fluid is in relation to its inertia. Essentially, it tells us how easily a fluid flows when viscous and inertial forces are at play. Think of it as the ratio between the viscous force trying to slow the flow and the inertial force trying to keep it moving. If we know the fluid's density, we can convert between dynamic and kinematic viscosity, which is really useful in practical applications. Kinematic viscosity is also similar to how quickly heat or mass diffuses through a substance, but in this case, it's the momentum diffusing. Next, we have dynamic viscosity, or what is often called absolute viscosity. This describes the relationship between shear stress and shear rate within a fluid. In simpler terms, it tells us how much force is needed to make a fluid slide past itself at a certain rate. It's fundamental because it impacts how fluids flow under different conditions. Both types of viscosity are crucial for understanding fluid behavior, especially when analyzing flow in pipes or around objects, which ties back to our overall theme of fluid dynamics. So, grasping these concepts helps us predict and control fluid behavior more effectively. There are two main types of viscosity that we need to understand: dynamic or absolute viscosity and kinetic viscosity. Let's start with dynamic or absolute viscosity, which is often denoted by the symbol P. The units for this are quite standardized. For example, 1 Pascal second or 1 PAS is equivalent to 1 kilogram per meter second, or 1 NSM2. Another common unit is the poise, where 1 poise equals 100 centipoise, or 0.1 Pascal seconds. Moving on to kinetic viscosity, which is a bit different. Its units are usually expressed in stokes, where 1 stokes equals 1 square centimeter per second, or 0.0001 square meters per second. It's important to understand the relation between these two types of viscosity. They are interconnected, with the dynamic viscosity being related to the kinetic viscosity through the density of the fluid. Understanding these two types and their units is fundamental, because they help us quantify how fluids resist flow and deformation, which ties directly into the overall theme of fluid dynamics we're exploring. Let's take a closer look at how viscometers are categorized based on their working principles. There are 3 main categories we should focus on. First, we have the rolling ball method, which measures viscosity by observing the movement of a ball rolling through a fluid. It's a simple yet effective way to determine the fluid's resistance to flow. Next is the pressure-driven method, where we analyze how a fluid responds to an applied pressure. This method is particularly useful for fluids that are difficult to test with other techniques, because it relies on pressure differences to gauge viscosity. Then we have capillary methods, which involve passing a fluid through a narrow tube or capillary. The flow rate and the time it takes the fluid to pass through the capillary give us valuable information about its viscosity. Additionally, there's the rotational method. In this approach, a device rotates a spindle or cylinder submerged in the fluid, and the torque needed to maintain that rotation reveals the fluid's viscosity. All these methods are different ways to measure viscosity, depending on the specific application or fluid type. They connect to our overall theme by showing how diverse and adaptable our tools are for understanding fluid flow properties. Each method has its unique advantages and is chosen based on the particular requirements of the measurement task. Let's take a closer look at the basic design of a rolling ball viscometer. It essentially consists of a tube or capillary that holds the sample liquid we're testing. Inside this tube, there's a ball selected carefully so that it takes at least 20 seconds to roll through the sample when measured at a specific angle. This minimum time helps ensure accurate and consistent viscosity measurements. Now, the rolling ball method is primarily used for Newtonian fluids. These are fluids whose viscosity remains constant regardless of how fast or how much you shear them. So whether you're applying a gentle or vigorous force, their viscosity doesn't change. This method is quite straightforward and reliable for such fluids because it relies on measuring the time it takes for the ball to roll through the liquid. The key here is the design, choosing the right ball and angle to get meaningful, reproducible data on the fluid's viscosity. So, in summary, The design of the viscometer and the method itself are tailored to accurately determine the viscosity of Newtonian fluids by observing the rolling behavior of a ball within a controlled setup. Now, let's discuss pressure-driven methods for measuring viscosity. These methods are quite versatile because they can be used for both Newtonian and non-Newtonian fluids. That means whether the fluid's viscosity stays constant or changes with shear rate, these methods can handle it. The devices involved include slit viscometers and rheometers, which are designed to provide accurate measurements under different conditions. Additionally, we have capillary extrusion viscometers. Focusing on capillary viscometers, as explained in the section on viscosity, capillary methods, these devices operate on a simple but effective principle. The flow of the fluid is driven by gravity. Essentially, the fluid moves through a narrow tube or capillary because of the gravitational force acting on it. Because of this, capillary viscometers are categorized under pressure-driven methods. They rely on the pressure difference created by gravity to measure how easily the fluid flows, which in turn gives us its viscosity. Now, specifically looking at slit viscometers and rheometers, these tools are designed to analyze fluids under different flow conditions. They help us understand how fluids behave when subjected to shear stresses, providing detailed insights into their viscosity characteristics. Overall, pressure-driven methods, including these devices, are crucial in many industrial and research applications because they offer reliable, straightforward ways to measure viscosity across a wide range of fluids and conditions. Now, let's look at the two main types of capillary viscometers. First, we have method I, the suspended level or ubaload type capillary viscometer. This method involves a vertical tube where the fluid's flow is measured by observing the time it takes for a small amount to pass between two marks. It's known for its accuracy and is commonly used in precise viscosity measurements. Next, method II is the simple U-tube or Ostwald type capillary viscometer. This one is a bit more straightforward. Imagine a simple U-shaped tube where the fluid's flow rate is determined by measuring the time it takes for the liquid to move from one mark to another. Both these methods rely on capillary action, where the flow characteristics are directly related to the fluid's viscosity. In addition to these, there's the rolling ball method, which is particularly useful for Newtonian fluids, those that have a viscosity independent of the shear rate. In this method, a ball rolls down a capillary tube, and by measuring its speed, we can determine the viscosity of the fluid. All these methods are crucial because they help us accurately measure viscosity, which is key in understanding a fluid's flow behavior under different conditions. They connect to our broader goal of characterizing fluids for various industrial and research applications. The principle of the rotational method is to measure the force, or torque, acting on a rotor when it rotates at a constant angular velocity, or rotational speed, in a liquid. This approach is fundamental because it allows us to determine the viscosity of fluids by observing how much torque is required to keep the rotor spinning steadily. Rotational rheometers and viscometers are the main tools used here. They're versatile because they can measure the viscosity of both Newtonian and non-Newtonian fluids. For Newtonian fluids, the viscosity remains constant regardless of the shear rate, so the measurements should be consistent across different rotational speeds within experimental error. When dealing with non-Newtonian fluids, we often look at the apparent viscosity, which can change depending on the shear rate. So, understanding the behavior under different conditions helps us characterize these more complex fluids. Another key point to remember is temperature control. Since viscosity is highly dependent on temperature, the sample's temperature should be maintained within plus or minus 0.1 degrees Celsius, unless specified otherwise. This ensures accuracy and reproducibility in our measurements. Overall, the rotational method is a reliable technique for characterizing fluid viscosity, provided we control variables like temperature and understand the fluid's rheological behavior. Let's take a closer look at the different types of viscometers used to determine viscosity through the rotational method. First up, we have the spindle viscometers. These are simple and versatile devices where a spindle rotates inside the fluid, and the resistance to rotation gives us the viscosity measurement. Next, we have the concentric cylinder rheometers. In this setup, a cylinder rotates inside a stationary cylinder, or vice versa, and the shear stress is measured to determine viscosity. This method is particularly useful for fluids with a wide range of viscosities. Moving on, there's the cone end plate rheometers. Here, a cone is positioned close to a flat plate, and the fluid is placed in the small gap between them. When the cone rotates, the shear rate is uniform across the sample, making it ideal for precise viscosity measurements, especially for small sample volumes. Finally, we have the parallel plate, or parallel disc rheometers. This setup involves two parallel plates with the fluid sandwiched in between. As one plate rotates, we measure the torque required, which directly relates to the fluid's viscosity. All of these instruments operate on the rotational method, which is a powerful way to assess how fluids respond to shear forces. They allow us to evaluate complex fluids with accuracy and are fundamental tools in our viscosity measurements. Understanding these types helps us choose the right viscometer for specific samples and conditions, ensuring reliable and meaningful results. Let's take a closer look at the types of spindles used in the apparatus. As you can see in Figure 1, we have cylinder-shaped spindles, and in Figure 2, there are disc-shaped spindles. These are the key components that interact with the liquid during viscosity measurements. The apparatus involves immersing these spindles into a large volume of liquid and rotating them to determine the apparent viscosity. The rotational method, specifically method I using spindle viscometers, relies on this principle. By rotating the spindle, whether it's cylindrical or disc-shaped, we can measure how the liquid resists flow, which is essentially its viscosity. The shape of the spindle affects the flow pattern and the measurement accuracy, so choosing the right type is important depending on the liquid properties. In essence, these spindles are designed to provide consistent, reliable readings by rotating within the liquid and allowing us to interpret the resistance as viscosity. This method is fundamental in many industries for assessing fluid behavior under different conditions. Let's look at the rotational method, specifically Method I, which involves spindle viscometers. Now, an important point to remember is that we can't directly calculate the absolute viscosity using this method. That's mainly because of the large gap between the spindle and the container wall, or sometimes because of the shape and geometry of the spindle itself. What we do measure, however, is the torque needed to keep the spindle turning at a certain angular velocity. This torque gives us an idea of the liquid's resistance to flow, but it's more accurate to call it an apparent viscosity rather than a true, absolute value. It's also worth noting that other types of spindle viscometers can be used, as long as they provide accuracy and precision comparable to the ones described here. Essentially, the goal is to ensure consistent and reliable measurements, regardless of the specific spindle type, so long as they meet the quality standards outlined in this chapter. Now, let's talk about the rotational method, specifically Method I, which involves spindle viscometers. When we measure viscosity using this method, especially in a beaker or cup, it's important to recognize that the shear rate we apply isn't always known beforehand. To ensure that our results are reproducible across different labs and instruments, we need to report certain parameters alongside the viscosity value. These include the size and geometry of the spindle we use, as well as the angular velocity or rotational speed at which the spindle turns. Additionally, recording the temperature of the test substance is crucial, since viscosity is highly temperature-dependent. When setting up the test, make sure the spindle is immersed to the recommended depth, maintaining at least a 1 centimeter clearance from both the bottom and the sides of the container. Proper preparation of the specimen, including bringing it to the correct temperature, is also essential and should follow the specific instructions outlined in each monograph. Finally, always adhere to the manufacturer's recommendations regarding sample loading, spindle selection, and operation of the viscometer. These steps help ensure accurate, consistent, and comparable viscosity measurements across different settings. Now, let's talk about the calibration process for the rotational method, specifically using spindle viscometers. First, it's important to check the calibration of your viscometer at the test temperature. To do this, you'll use fluids with known viscosities, often called Newtonian viscosity standards. The key here is to choose calibration standards that bracket the expected viscosity of your sample. Basically, your standards should be slightly higher and lower than what you expect your sample's viscosity to be. This way, you can ensure your measurements are accurate across the range you're working with. Remember, a viscometer is considered properly calibrated if the apparent viscosities you measure are within plus or minus 5% of the standard values. Also, to maintain accuracy and consistency, it's best to follow the manufacturer's recommendations for calibration, operation, and cleaning. This ensures your viscometer performs reliably over time, helping you get precise, reproducible results that are essential for your analysis. Now let's look at the rotational method, specifically method II, which involves concentric cylinder rheometers. In this setup, the key idea is that we determine the apparent viscosity by placing the liquid sample in the gap between two cylinders, an inner and an outer one. This setup allows us to measure how the fluid responds under shear. Both controlled stress and controlled rate rheometers are commercially available for this configuration. They typically feature very small annular gaps, which are essential for accurate calculations, especially when working with non-Newtonian fluids whose viscosity can change under different conditions. Controlled shear stress rheometers work by applying a specific force or torque to generate shear, and then measuring the resulting shear rate. Conversely, controlled shear rate rheometers do the opposite. They set a particular shear rate, like a rotational speed, and then measure the shear stress that develops from that. Sometimes, these types of rheometers are called cup-and-bob rheometers because of their design. An important consideration is whether the outer cylinder, known as the cup, or the inner cylinder, called the bob, is the one that rotates. This choice influences the system's behavior and is key to the experiment's setup. When the cup rotates, we refer to the system as a Couette cell, whereas if the bob is rotating, it's called a Searle system. Recognizing these distinctions helps us understand the specific mechanics and how to interpret the data correctly. Overall, this method is versatile and widely used because it effectively measures complex fluid behaviors, which ties into our broader goal of understanding material rheology through different experimental approaches. Let's take a closer look at some specific types of rotational rheometers, starting with the Searle concentric cylinder system. This setup uses a cylinder within a cylinder, where the inner cylinder rotates to measure the fluid's response. It's particularly useful for testing more viscous materials or suspensions. Next, we have the Couette concentric cylinder system, which is quite similar but with some differences in design and application. It also involves two cylinders, with the sample placed in the gap between them. When the outer or inner cylinder rotates, we can analyze the material's flow behavior under shear. Both of these are examples of what we call the rotational method, specifically method II, which involves these concentric cylinder rheometers. This method is widely used because it provides detailed insights into the viscoelastic properties of fluids and soft solids. Overall, these systems are essential tools in rheology, helping us understand how materials deform and flow under different conditions. They connect directly to our goal of characterizing complex fluids for various industrial applications. Let's walk through the procedure for using a rotational method with concentric cylinder rheometers. First, you'll need to place a sufficient amount of test fluid into the rheometer and allow the sample to reach thermal equilibrium. This step is crucial because consistent temperature conditions ensure accurate viscosity measurements. You can check for equilibrium as indicated in the individual monograph for your specific material. Next, operate the rheometer according to the manufacturer's recommended procedure. It's important to follow their guidelines closely to ensure proper functioning and reliable data. For non-Newtonian systems, the monograph will specify the type of rheometa you should use, as well as the shear rates at which you need to perform measurements. This helps capture the material's complex flow behavior accurately. Then, you'll determine the apparent viscosities by varying the shear rate or shear stress if you're using a controlled shear stress rheometa over an appropriate range. This range should reflect the conditions relevant to the material's intended use. By doing this, you can gather a series of viscosity measurements at different shear conditions. From these measurements, you'll be able to establish the relationship between shear rate and shear stress for the non-Newtonian liquid. This relationship is key to understanding how the material behaves under different flow conditions. Now, let's quickly review some of the key parameters involved in this process. The torque acting on the cylinder surface is denoted as m, measured in Newton meters. The radius of the outer cylinder is r0, and the inner cylinder's radius is r1, both in meters. The height of the inner cylinder immersed in the liquid is h. The angular velocity, which is the rate at which the inner cylinder rotates, is omega, expressed in radians per second. Viscosity itself is represented as eta, measured in Pascal seconds, and v is the linear velocity in meters per second. In summary, this rotational method using concentric cylinder rheometas allows us to characterize the flow properties of complex fluids comprehensively, which is essential for many applications across industries. Now, let's take a closer look at the cone-end plate rotational rheometa with a rotating cone. In this setup, the liquid is introduced into the small, fixed gap between a flat plate or disc and a cone that forms a specific angle. This design is quite clever because the cone's angle ensures that, as you move away from the center, both the gap and the linear speed increase proportionally. This means the shear rate remains constant throughout the measurement, which is a key advantage for accurate viscosity testing. You can measure viscosity by rotating either the cone or the plate, depending on the specific configuration or material you're testing. This rotational method, often referred to as method III, is widely used because it provides reliable, consistent results for a variety of fluids. Overall, this setup helps us understand how fluids behave under shear, which is essential for many applications across industries. Let's take a closer look at the cone-end plate rotational rheometa with a rotating plate. This setup is a key part of method III, which is used to measure the flow properties of fluids. In this configuration, the plate or cone rotates at an angular velocity, which we denote as omega, measured in radians per second. The torque, represented by m, acts on the flat plate or cone surface and reflects the fluid's resistance to flow. The angle alpha is the angle between the flat plate and the cone, and it's measured in radians. This angle influences the shear rate applied to the fluid during testing. The radius of the cone, r, is an important geometric parameter, measured in meters, as it determines the surface area interacting with the fluid. Overall, this rotational method allows us to precisely analyze the rheological behavior of complex fluids by controlling the shear conditions and measuring the resulting torque. It's especially useful because it provides a uniform shear rate across the sample, leading to accurate and reliable data. Understanding these key parameters helps us interpret the fluid's flow characteristics, which is central to our broader goal of characterizing material behavior under different conditions. Let's take a closer look at the parallel plate rotational rheometa. In this setup, the key parameters include omega, which is the angular velocity measured in radians per second, and r, the radius of the plate given in meters. There's also h, the distance between the two parallel plates, also in meters. This type of rheometa is quite similar to the cone-end plate design, but instead of a cone, we use two flat plates or discs. The sample to be measured is placed in the gap between these two parallel plates. Typically, during measurement, the lower plate remains stationary, while the upper plate rotates at a constant angular velocity, which we denote as omega. The rotational method, or method IV, involving parallel plate or parallel disc rheometers, is particularly useful because it allows us to analyze the flow and deformation behavior of materials under shear. Understanding these parameters and the setup helps us interpret how the material responds under shear stress, which is central to rheology. So, by controlling the rotation and measuring the response, we gain valuable insights into the material's properties. These viscometers are versatile tools that can be used for both Newtonian and non-Newtonian systems, which is really important because it means they can handle a wide range of fluids. Among the various types available, these are some of the most widely used in industry and research, thanks to their reliability and simplicity. One of the key advantages is their very simple construction, making them easier to operate and maintain compared to more complex viscometers. Now, specifically, we're talking about the rotating concentric cylinder viscometer. This type works by rotating one cylinder inside another, which allows us to measure the fluid's resistance to flow or viscosity. Overall, their straightforward design and broad applicability really contribute to their popularity in many applications, helping us better understand fluid behavior in different systems. Now, let's take a closer look at spindles and sample chambers. These are essential components in viscosity measurements. When we use a rotating concentric cylinder viscometer, the spindles are the parts that actually rotate within the sample. They come in different types and sizes, depending on the specific material we're testing. The design of the spindle affects how accurately we can measure viscosity. Sample chambers, on the other hand, are where we place our sample. They need to be well designed to ensure uniform flow and temperature control. Proper chamber design minimizes errors and ensures reliable results. Overall, understanding the role of spindles and sample chambers helps us appreciate how precise and consistent viscosity measurements are achieved with this type of viscometer. These components are crucial for obtaining accurate data, which in turn supports our broader goals of quality control and material characterization. Let's take a closer look at the rotating concentric cylinder viscometer and its different types. This device is quite essential when it comes to measuring viscosity, and understanding the variations helps us select the right method for specific materials. First, there are primarily two main types, the steady shear and the oscillatory type. The steady shear viscometer measures viscosity under constant shear conditions, giving us insight into how a fluid flows under continuous stress. These are often used for liquids with relatively uniform flow behavior. On the other hand, oscillatory viscometers apply a back-and-forth or oscillating motion, which is particularly useful for analyzing complex fluids like polymers or biological materials. They help us understand how these materials respond to dynamic forces, revealing properties like elasticity and viscoelasticity. Both types involve rotating cylinders, but the way they are used and the kind of data they produce differ significantly. The choice between them depends on the nature of the material and the specific rheological properties we're interested in. So, understanding these types allows us to better interpret the material behavior, which ties into our overall goal of characterizing fluids accurately for various industrial and research applications. Now, let's take a closer look at the construction of this type of viscometer. At its core, it involves a lower cylinder, which we refer to as the cup, and an upper cylinder, known as the bob. The liquid under test is placed between these two cylinders. The lower cylinder is set to revolve, and this motion is crucial for measuring viscosity. To achieve this, the lower cylinder is connected to a motor via a pulley, ensuring it rotates at a constant angular velocity. Maintaining this steady rotation is vital for accurate measurements. The upper cylinder, or bob, is attached to a torsion wire, which provides a restoring torque as the bob resists the movement caused by the liquid's viscosity. As the lower cylinder turns, the liquid's resistance causes the bob to rotate slightly, and this movement is transmitted through the torsion wire. A scale and pointer system then help us measure this angular displacement. By analyzing the torque and the angular velocity, we can determine the viscosity of the liquid under test. Overall, this design allows us to precisely measure how a liquid resists flow under controlled conditions, which is fundamental for understanding its rheological properties. Let's delve into the principle behind the rotating viscometer. At its core, it relies on Newton's law of viscosity, which is fundamental to how it operates. The idea is that the fluid we're measuring is sheared between two surfaces. Think of it like having a thin layer of fluid in between two plates. One of these surfaces stays still, while the other is rotated by an external drive. The fluid fills the space in between these surfaces, and as the rotating surface moves, it exerts a shear force on the fluid. Now, during measurements, we can approach this in two ways. Either we apply a constant torque and observe how the speed of rotation changes, or we keep the rotation at a constant speed and measure how much torque is required to maintain that speed. This flexibility allows us to accurately determine the fluid's viscosity. Specifically, in a rotating concentric cylinder viscometer, the principle remains the same. The fluid is sheared between the inner and outer cylinders, with one rotating and the other stationary. By analyzing the torque and rotational speed, we gain insights into the fluid's viscosity. This method is crucial because it helps us understand the flow characteristics of different fluids, which ties directly into the overall theme of characterizing fluid behaviors through various viscometers. Now, let's take a look at how the applied torque from the motor plays a crucial role in the operation of the rotating concentric cylinder viscometer. Essentially, the motor applies a torque to rotate the inner cylinder, and this torque is directly related to the viscosity of the fluid being tested. The more viscous the fluid, the greater the torque needed to keep the cylinder rotating at a constant speed. This principle is fundamental because it allows us to measure viscosity indirectly by monitoring the torque. So, when we talk about the working principle of this device, we're focusing on how the motor's torque correlates with the fluid's resistance to flow, giving us valuable data on the fluid's properties. This connection between applied torque and fluid behavior is at the heart of how the viscometer provides accurate, reliable measurements. Now let's look at how the rotating concentric cylinder viscometer works. It measures the torque needed to rotate an immersed element, which we call the spindle, within a fluid. Essentially, as the spindle turns, it encounters resistance from the fluid, and this resistance is related to the fluid's viscosity. The spindle is driven by a motor, but what's interesting is that it's connected through a calibrated spring. This spring allows us to measure the deflection or tension, which we can see on a digital display. What's key here is that, for a given viscosity, the drag or resistance to flow, that is, how much the fluid opposes the spindle's rotation, is directly proportional to the spindle's speed. So, the faster we rotate, the greater the resistance, and this proportionality helps us determine the viscosity accurately. This setup is a practical way to assess fluid flow properties, linking the mechanical torque to the fluid's internal resistance, and it ties directly into our overall theme of understanding fluid behavior through precise measurement tools. Today, I'll be explaining the working principle of the rotating concentric cylinder viscometer. This device is crucial for measuring the viscosity of fluids in a precise and reliable way. Essentially, it involves two cylinders, one nested inside the other, which rotate relative to each other. The outer cylinder is usually fixed, while the inner one rotates at a known speed. As the inner cylinder turns, it exerts a shear force on the fluid sandwiched between the two cylinders. This shear force depends on the fluid's viscosity. By measuring the torque required to rotate the inner cylinder at a specific speed, we can determine the fluid's viscosity accurately. This method is especially useful because it mimics real-world flow conditions and provides consistent, reproducible results. Throughout this presentation, understanding this principle helps us appreciate how viscosity measurements are performed in practical applications. Before starting any testing, the system must be properly leveled. This is a crucial step to ensure accurate and reliable results. Next, you'll want to select the spindle and set it in the control panel before initiating the test. Proper setup here helps maintain consistency throughout your measurements. When taking readings, make sure the temperature is stable and constant. This is vital because temperature fluctuations can skew your data. During observation, the torque should be within the range of 10 to 90%. Keeping it within this window ensures that the test conditions are optimal and that the results are meaningful. I also highly recommend using Riacalc software for readings instead of manual measurements. This software simplifies data collection and increases accuracy. Whenever possible, try to take readings starting from higher temperatures and moving to lower ones. This approach helps in better understanding the behavior of the material across temperature ranges. And finally, always keep safety and accuracy in mind. Follow these precautions to ensure your testing process is both safe and effective. Now let's talk about method precision, specifically intermediate precision. When we're evaluating our method's consistency, one key aspect is intermediate precision, which essentially looks at how reproducible our results are across different days, analysts, or equipment. The acceptance criteria here is that the percentage relative standard deviation, or %RSD, should not exceed 5%. This threshold helps us ensure that our method remains reliable and consistent over time and under varying conditions. A crucial point to keep in mind is that we need to be cautious about maintaining this precision. Variability beyond this limit could indicate issues with the method or the process, so it's important to monitor and control factors that might influence the results. In the context of overall method validation, achieving and maintaining this level of precision confirms that our method is both robust and suitable for routine analysis. So always remember, keeping our intermediate precision within these criteria is vital for ensuring the quality and reliability of our analytical results. When we look at pharmaceuticals, the viscosity of creams, lotions, suspensions, and gels plays a crucial role in how they are absorbed by the body. Basically, the thicker or more viscous these products are, the slower the active ingredients tend to be released and absorbed. Conversely, a softer, less viscous base generally allows for a greater release of active ingredients, which can improve efficacy. Now, for semi-solid products like creams and gels, viscosity doesn't just influence absorption directly. It also affects how the active ingredients diffuse through the product, which ultimately impacts how well they penetrate the skin or target tissues. When it comes to suspensions, viscosity is especially important for stability and pourability. If the suspension is too viscous, it might be difficult to pour or dose accurately. If it's too thin, it could separate or settle quickly, compromising the product's stability and uniformity. Beyond pharmaceuticals, viscosity considerations are also key in industries like food, where it influences texture and mouthfeel, lubricants, where it affects performance, paints, where it impacts application and finish, and even in advanced areas like 3D printing, chemicals, and detergents, where viscosity determines flow and mixing properties. In essence, understanding and controlling viscosity is vital across these applications because it directly impacts product performance, stability, and delivery. It's a fundamental factor that ties into the overall theme of optimizing formulation and application for best results. Let's talk about formulation changes and how they can influence asphalt behavior. One of the key ways we can assess this is through viscosity measurement. It's a useful tool to understand how modifications in binder formulation might affect performance. Moving on to aging phenomena, binder aging is a critical aspect, and we can evaluate it by observing changes in viscosity. As the binder ages, its viscosity tends to increase, which can impact its flexibility and durability over time. Now, regarding production temperature, viscosity measurement helps us determine the optimal mixing and compaction temperatures for asphalt concrete. Ensuring the right temperature is vital for proper workability and compaction, which ultimately affects the quality of the pavement. Lastly, the effect of processing can be assessed through viscosity. This allows us to see how different processing conditions influence the binder's properties, helping us optimize the manufacturing process for better performance. In summary, viscosity measurement is a crucial tool because it provides insights into formulation, aging, production, and processing effects, making it essential for ensuring the durability and quality of asphalt pavements. Now, moving on to the references section. Here, I want to highlight some key points about the operation and calibration of viscometers. We've looked at different types, including the Fungi Lab Visco Basic, as well as Brookfield, Synchroelectric, and AIMTech models. The main idea is that proper calibration is essential to ensure accurate viscosity measurements. The USB chapters provide standardized methods for different viscosity measurement techniques. For example, USPNF 911 covers capillary methods, which are useful for measuring low-viscosity fluids with precision. Then, we have USPNF 912 for rotational methods, which are more versatile and commonly used in many laboratories. Next, USPNF 913 describes the rolling ball method, a simple yet effective technique especially for viscous liquids. And finally, USPNF 914 details pressure-driven methods, which are suitable for fluids that are difficult to measure with other methods. The key takeaway here is that understanding these chapters and the proper operation and calibration of your viscometer are critical for obtaining reliable data. Connecting this to our overall theme, precise viscosity measurements underpin quality control and formulation development in pharmaceutical manufacturing. Thank you so much for being here today. I really appreciate your time and attention. I hope you found this presentation insightful and helpful. Remember, the key takeaways are what we discussed about the importance of collaboration, innovation, and continuous learning. These concepts are essential for success in our field. I encourage you to apply what you've learned and keep pushing forward. If you have any questions or want to discuss further, please feel free to reach out. Once again, thank you for your engagement and participation. Have a great day.